So I'm going to talk about a recent joint work together with Johannes Ebert, who is a topologist. This will become visible during the talk, and Julian Kranz. And the motivation for this work is actually a theorem by Lacker and Spielberg from '96. That says that if you have, if G is a torsion-free hyperbolic group, then the cross products associated to the action of G on its boundary is determined up to isomorphism by the K-theory. So then the cross product C-star algebra is, if you like, classifiable by K-theory. All right. So this is actually comes from the fact that it belongs to a class of C-star algebras which we know are classifiable by K-theory, namely purely infinite C-star algebras. But that's so that's the result that motivated us to try and see whether we can compute the K-theory in some examples. And after we started working on that, turned out that some results are already known. So one such example is the work of Emerson and Meyer in 2004. Yes?
When you say classifiable, you mean classifiable by all elements invariants?
Just K0 group and the unit class and K1. In this case, the tracial data disappears. So one example is that you can, for the free group acting on its boundary, the K0 can be computed and is isomorphic to Z mod n minus 1Z and the copy of Z to the n. And the K1 group is just a copy of Z to the n. So definitely the K-theory already distinguishes these cross products, and therefore they are not isomorphic. And the goal of this project was to find examples where we know that the K-theory, where we can compute the K-theory and show that the K-theory is the same for class of examples, and then deduce that all these cross products must be therefore isomorphic by this theorem. Okay. So for that I have to tell you a little bit and maybe I say also that the theorem of Emerson and Meyer is much more general. This is only one example that they conclude. So I have to make some setting in order to say which examples we consider. So let's fix M to be a nice closed oriented connected three-dimensional hyperbolic manifold. And we will consider now the group G, which is just the fundamental group of M. And G acts canonically by Deck transformations on the universal cover of M. So now a G just by 1 of M by Deck transformations. Okay. So I want to analyze a little bit this action. So first of all, the universal of cover of M looks locally like M itself. So it's also a three-dimensional hyperbolic manifold. But since it's a universal cover, it's also simply connected. And therefore, there is only one such manifold, namely the three-dimensional hyperbolic space. So we conclude that M tilde is isometric to the three-dimensional hyperbolic space. And now the action of G on the universal cover is also a proper action, which in our case is also co-compact. Because of our assumption, I mean the orbit space of this action is always the base space, namely M, and we assumed that M is compact. In this case, by Milnor-Schwarz lemma, when you have such an action, proper and co-compact action, then G, the acting group, looks essentially the same like the space it's acting on, namely it's quasi-isometric to the space it's acting on. And so G, by Milnor-Schwarz lemma, G is quasi-isometric to M tilde. And since quasi-isometry preserves hyperbolicity, also now G is a finitely generated hyperbolic group. And so G is hyperbolic. And also, if you have such a quasi-isometry, then it's known that the Gromov boundaries will be homeomorphic. And since M tilde is just the three-dimensional hyperbolic space, its boundary is the two-sphere. Okay. So that's the first thing we need to know. The next observation is that the action now is also a free action on a contractible space, because again H3 is contractible. And whenever you have such an action, essentially by definition, the orbit space is a model for the classifying space BG. So now, thus, the orbit space, which in our case is just M, is a model for BG. Finally, I also want to observe that the group G is torsion-free. This is because if you look at the cohomology groups of G, this is isomorphic to the cohomology groups of the classifying space BG. And since the classifying space is just a finite dimensional manifold, the cohomological dimension is finite. I mean, from some point on, all the cohomology groups will disappear. And now, so the cohomological dimension of G is finite, and therefore also every subgroup of G will have finite cohomological dimension. Thus, it cannot admit any cyclic subgroups. They have infinite cohomological dimension, and so it must be torsion-free. Now, the goal will be to compute the K-theory of the cross products for these actions. And we are going to use maybe I do it on the next blackboard. So we are going to use the result of Emerson and Meyer from the same paper, which says that there are short exact sequences in K-theory of the following form. Where here is the canonical inclusion of the reduced group C-star algebra inside of the cross product, and the quotient is K1BG. And similarly for K1 of the cross product, has a normal subgroup K1 of the reduced group C-star algebra, and as a quotient K0 of BG. So the idea of how to get such short exact sequence is actually interesting, and maybe I will comment about it at the end if I have time. But assume for a moment that we have such short exact sequences and we want to compute the K-theory, namely the middle term here. What we have to know is how to compute the K-theory of the classifying space, namely the K-theory of the manifold M. And now we use that Baum-Cohn conjecture holds for such groups, torsion-free discrete hyperbolic groups, to know also that the K-theory of the reduced group C-star algebra is the same as the K-theory of the a classifying space, I mean the K-homology. And so K1 of M. And then we would want to compute the K-homology and the K-theory of the manifold. And then we will find conditions under which these short exact sequences split, so that the K-theory of the cross product is just a direct sum of this part and that part. So in order to compute the K-theory of and the K-homology of the manifolds, we have to use a Atiyah-Hirzebruch short exact spectral sequences. Sorry. So, and I will tell you a little bit about that. Instead of defining spectral sequences, I will do it directly through these examples. Okay, so okay, now I will try to explain. So a spectral sequence in general, in this case in particular, is given by pages, where the number of the page is this index here. So here we are describing the second page of the spectral sequence. And every page essentially is just a grid of abelian groups, at least in the category of abelian groups. The second page is given by these abelian groups, where the PQ denote the coordinates. And so we know that to place PQ, we will have this abelian group in the grid. So, and also we are going to use that the K-theory of a point is Z if Q is even and 0 otherwise. So that the grid we get looks like this. So this is the 0 level, 1, 2, 3. So if P, namely if on the x-axis we are on the negative side, namely if P is negative, then the negative cohomological groups are just vanished. So on the left-hand side, this is all zeros. And now on the right-hand side, in the 0, 0 coordinate, we just get H0 of M with coefficients in Z, namely just H0 of M. So this is the visualization of this spectral sequence. And then again, for Q just being 0, we get all the time coefficients in Z, and so we just get the cohomology groups of the manifold. And since we're dealing with a three-dimensional manifold, after the third cohomology group, all of them will vanish. So we have only finitely many non-zero columns. And now for Q odd, as we said, this is just a 0 because the coefficients disappear. And for Q being 2, it's even, so it's repetitively just the cohomology groups of the manifolds. And once more. And now the spectral sequence is also equipped with maps between these coordinates called differentials. And the differentials, in general, the differentials denoted di, will go, so on the second page will go one step down and 2 steps to the right, so something like this. Okay, so I guess this comes from there. Yeah. Or more generally from the, so let's see, so from the PQ coordinate to the P plus I, this means 2 steps to the right, I steps to the right, and I minus 1 is down. Okay, so in our case, since all the differentials, I mean, they move from odd rows to even rows, and from even rows to odd rows, they either have a domain which is 0, or they have an image which is 0. Therefore, all these differentials will always just be 0, the 0 maps. So if you like. And I haven't said also that the condition is that if you compose them, whenever you can compose them, you get 0. So if you compose this one and go on with this one, then it must be the 0 map. That's another condition. And the next page, in our case, the third page, is just the homology of the second page. So in other words, E3 is the kernel of di, and I have to specify coordinates, but I'm not doing it here because it doesn't add much information. But if you want to get in the third page this coordinate, you have to consider the kernel of this map divided by the image of this map, which is fine because the kernel contains the image. Okay, so in our case, since all these differentials disappear, the third page is just again the second page. Nothing happens, right? And now what's not so clear is now that when you consider differentials on the third page, you will have maps that go 2 steps down and 3 steps to the right, so something like that. And theoretically speaking, this can be non-zero, right? That's the only possibility where this can be non-zero map. And one can check that it's also 0. So D3 is also 0. And now if you go to, so the fourth page will again as a grid be just the second page or the third page. but the differentials now just will go beyond the amount of columns that we have that are non-trivial, and therefore the next differentials will always just vanish. So in that case, when all differentials vanish from some point on, maybe I use that word, we can define the infinity page, or the limiting term, to be the last page which was the interesting one, so namely in our case just E2. And this, here we don't have differentials, we just have the grid. Now, Atiyah-Hirzebruch's theorem says that this spectral sequence, defined like this, converges to the P plus QK theory of the manifold. So now using this spectral sequence, we want to compute the K theory of the manifolds, and that's the key for it. And we have to do this in the case of P plus Q being 0 and P plus Q being 1. So let's focus just on the case that that we want to compute just the case P plus Q equals 0, namely maybe I write just P minus P, because if they sum up to 0, then Q is just minus P. And now I have to interpret what this convergence means. This convergence means that, that there exists some filtration of this limit term of this K0 of M. So there exists some filtration so descending normal subgroups, where, which is also housed off, namely the intersection of all of these GP vanishes. And E infinity P minus P is just given by GP GP divided by GP plus 1. Okay. So the grading is maybe not given explicitly, but now that we know this condition, we can read it off. So yeah. So what does it mean? It means that G0, namely K0 of M, has as a normal subgroup G1, and the quotient exactly by this formula is E infinity 0, 0. And this is our K0 of M. And we go on like this, so we will have finitely many steps, and we will discover inductively what these gradings are. So G1 has a normal subgroup G2, and the quotient G1 divided by G2 is E infinity 1 minus 1. And we have to do a little more. And one more. So in our grid, we are looking on P plus Q being equal to 0, namely on this diagonal here. This is 0. Okay, So infinity 0, 0 is just h0 of m, that's coordinate. Infinity 1 minus 1 will vanish, and infinity 2 minus 2 will be again h2. So we have to write this down. Maybe I actually start from below. 3 minus 3 will vanish. And also everything that comes later will vanish, right? 4 minus 4 and so on, because we go down the diagonal. And this means that G3 is isomorphic to G4. And from that point on, all these gradings will have to be isomorphic and will have to vanish because we know that the intersection of all of them vanishes. Okay, so G4 and G3 are also 0. This means that G2 is isomorphic to the 2 minus 2 coordinate, namely to H2. And so here it's also 0, and G1 is isomorphic to G2. So G1 is just H2 of M. So that's a bit, looks a bit technical, but I mean, it's just following these steps. And so in the first row, we just get a short exact sequence where K0 of M is in the middle, and we have as a normal subgroups H2 of M and as a quotient H0 of M. Now this means, since we are dealing with a connected manifold, the zero cohomology group just is Z, and therefore this first short exact sequence just splits, and we get from that the K0 of M is the H0 plus H2. One can carry a similar computation for P plus Q equal to 1 and get that the K1 of M is the H1 plus H3, so the sum of the odd cohomology groups. And I have to say that this is actually found to be due to Mattei in 2002. And in a way, you just get the isomorphism that you get from the Chern character, but instead for rational coefficients, you get it for integral coefficients. Now that we know that, we can come back to this short exact sequence here in order to see what is the K-theory, but we have to make still some assumptions in order to make sure that these short exact sequences split. And here I will now say what are the assumptions. So the theorem so let M be a three-dimensional hyperbolic manifold as above. And assume, moreover, that the first homology group of M is torsion-free. Since this is a finitely generated abelian groups, always this just essentially means H1 of M is just some Z to the D for some D. Then we get that the K-theory of the cross product is a Z to the 2D plus A2, also the K0 and also the K1. And one can also trace the class of the unit. So the class of the unit is mapped to the class of the unit in the K0 group. And so as a corollary, all these cross products by our classification theorem are isomorphic. So maybe I will explain shortly what is why it's a Z2D plus 2. So we come back to this short exact sequence, and we computed the K theory, but we didn't compute the K homology. Yes.
Because there is no shift of dimension between K theory of BG and the K theory of system reduced to G. It doesn't change much because the K0 and K1 are isomorphic.
I thought that this is like this. I mean, from the Baum-Kohn, I thought that this is the isomorphism from the K theory of the reduced group sister algebra to the K theory of the BG. Yes.
So there is a shift of dimension because here the
Okay.
dimension is 3. I have to think, but
yes. Okay, yeah. I have to think about that. Maybe I misread this, but
you have the action of the group G on C0 H3 and whatever is not element.
Yeah. Okay, so you say that here it should be K1.
It could be.
Yeah. Okay. I will believe that.
It doesn't change because
yeah, exactly. Yes. Okay, so here we will. So the K could be it's not needed, but the K homology of the manifold can also be computed either using the homological version of the Atiyah-Hirzebruch spectral sequence, or just using a kind of Poincaré duality for K theory, which in this situation just applies. So this is essentially what we have. And now K0 of M, as we said, is just H0 of M plus H2 of M. And H0 of M is isomorphic to Z plus Poincaré duality H1 of M, because it's a three-dimensional manifold. And then our assumption just comes in that says that this is isomorphic to Z plus Z to the D. And another copy of Z plus Z to the D comes from this side. So altogether is Z of 2D plus 2. And now the question if there are any such manifolds which satisfy these conditions. And it's also essentially a combination of some known, I shouldn't push it, some known results. So I will try to so a corollary from that is that there exist infinitely many pairwise non-isomorphic hyperbolic groups, those that as we constructed, with the cross products all isomorphic. And the proof is essentially a combination of two things that are well known. So one, for one, we need, so if A is a fixed finitely generated abelian group, in our case you can take, in our case we take A to B Z to the D, then a result of a Brock and Dunfield says that you can find there exist infinitely many pairwise non-isometric manifolds, three-dimensional hyperbolic manifolds, as we, with all the properties that we wanted. With the H1 group being just your fixed abelian group, namely in our case Z to the D. And now it still could be that the groups that we associate to them, namely the fundamental groups, coincide, but now comes a Mostow's rigidity theorem that applies in this case. So by Mostow rigidity theorem, the hyperbolic groups that come as the fundamental groups are pairwise non-isomorphic. So now we apply the result in order to get such groups. So maybe another comment, when we computed this K-theory of the manifold, we also showed on the way that the K-theory of the reduced group C-star algebras for all these groups are isomorphic. So these are torsion-free discrete groups, and in general, it's not known whether the reduced group C-star algebra can distinguish them. And the usual method to distinguish them is to compute the K-theory, but here the K-theory wouldn't help because it's the same for all these groups. But that's probably hard to see whether they are isomorphic or not. And the next comment is that this would be nice now if these cross products were isomorphic for a good reason, namely for a dynamical reason, so some orbit equivalence or something like that. But actually, we conclude that these isomorphisms that come from classification are not at all from dynamical origin, and the systems are not at all orbit equivalent. So this comes as a consequence of a theorem of Renaud and Shirly that says that if you have two dynamical systems, if G acting on a X and H acting on Y are two minimal topologically free dynamical systems, then the following are equivalent. The dynamical systems are continuously orbit equivalent, which essentially means that there is a homeomorphism between X and Y, preserving the orbits in a nice way, in a continuous way. Second, the cross product C-star algebras are isomorphic, and the isomorphism preserves the canonical Cartans, namely the canonical maximal abelian C-star algebras inside. And the third equivalence is that the topological full groups of the systems are isomorphic groups. So topological full groups is a tool essentially that allows to associate a group with a dynamical system. And it's mostly interesting when the dynamical systems are actions on totally disconnected spaces or Cantor spaces. And whenever, because it requires some Klopen decomposition of the space, and whenever the actions are on connected spaces, these topological full groups are just the groups, the acting groups themselves. So in our case, the actions are all the time on the boundary. So in our case, the actions are all the time on the boundary, and the boundary for all these groups is just the two sphere is always connected. And so these topological full groups are just the groups themselves, and we chose them so that they are not isomorphic. So the third condition fails, and therefore this means that the systems are not orbit equivalent, and the Cartan subalgebras are not preserved. Or in other words, these cross products contain infinitely many pairwise non-conjugate Cartans, all of them with the spectrum being the two sphere. Okay, I think I stop here. Thank you very much for your attention.